Hi, hello students. Welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Aneel Surampudi, and in this session, we are going to discuss about how the memory can get saved by using multi-level page table. So please like and share the session and subscribe to the channel if you haven't already yet. So let us start and get into the details. This is my experience, all about my experience. I do have a total of 13 plus years of experience, and I taught everywhere in India, including Andaman and Nicobar, and a triple post-graduation holder. And I'm a triple post-graduation holder. So let us start without wasting any more time. So this session focuses on what are the problems that we may face whenever we use a single level page table, and how we are going to construct a page table also we are going to understand. Single level page table as well as the multi-level page table. So let us start. But before that, before we enter into any of the details of this page table, let us brush up the concept of the virtual memory. What is virtual memory? You might have heard about the virtual memory already, but let me give you a glimpse of virtual memory again. What is virtual memory? You know that every time when you are working with the computer system, you do have a physical memory and you do have a secondary memory. The only available memory from the CPU's perspective for the CPU is the main memory. It's not the secondary memory. But in the virtual memory systems, CPU always thinks that the secondary memory is its physical memory. For instance, I do have a total of 1 MB physical memory and 20 MB secondary memory. Generally, this is what the physical memory that is available to the CPU, but in the virtual memory systems, CPU is given an illusion that the total physical memory that is available to it is the size of the secondary memory itself, but it is only secondary memory. We know that secondary memory can never get accessed by CPU directly. The only available memory is always the physical memory which is connected onto the CPU's motherboard, right? Now, what is virtual memory? First of all, we know that the physical memory is connected to the CPU motherboard. That is the only available memory for a programmer or a CPU. Virtual memory, in the virtual memory system, programmer imagines that the total secondary memory is his physical memory. The programmer, whenever a program is being constructed by a programmer, he needs to design the addresses. He needs to provide an address length. That address length must be equal to the number of address digits that are needed to represent the main memory. But in the virtual memory systems, the programmer thinks that he has the total main memory which is equal to the secondary memory. For an instance, for an example, let us understand. This is my secondary memory. The secondary memory size is, let us say, 1 MB. In order to represent 1 MB, I do require 20 digits, since 1 MB is equal to 2 power 20. And system also has a physical memory. It has to have a physical memory. Now the size of the physical memory, I will say main memory, which is equal to 32K. In order to represent any address within the main memory which is equal to 32K, I do require 15 digits, right? Since 32K is equal to 2 power 15. Here, simple. If you think sensible, obviously we always use the physical address. CPU uses only the physical address. But in the virtual memory system, CPU will imagine that the total secondary memory is its primary memory. So rather than using a 15-bit address, CPU uses a 20-bit address. By thinking that this is the actual memory which is at its disposal. This is all about virtual memory concept. Now understand what the page table. The table which is needed to locate the page needed by the CPU in the main memory, which page is available in which block. Now understand, when you talk about the secondary memory and the primary memory, both of these memory chunks are going to get divided into equal sized blocks. A block in the secondary memory is called a page. A block in the primary memory is called a block. Now we need to understand which page of the secondary memory is available at which block of the main memory. So let us understand carefully. Generally, a single level page table is used. We're going to understand how a single level page table is constructed and used, and what are the implications that we may face whenever we're using a single level page table. So let us understand by using a simple page table. For an instance, in order to appreciate this concept, I am using a secondary memory, an example of a secondary memory. This is my secondary memory and a main memory. Okay. My secondary memory has a total of 16 blocks. And the main memory is of, let us say, 8 blocks. Sir, what is a page? Page is nothing but a block in the secondary memory. In order to distinguish in between main memory block and the secondary memory block, we will refer to the block of the secondary memory as a page. We will refer to the block of the main memory as a block or a frame. So, one block in the main memory can be called as either a frame or a block, whatever you call. But one block in the secondary memory will be called as a page. Now, how many pages are in the secondary memory? There are altogether 16 pages. But now, you need to understand, you have to understand that no matter what, even if you turn the world upside down, CPU can never directly access the secondary memory at all. Why? Simple. If a data element is accessed from the main memory within 7 clock cycles, same data element may take 7 lakhs clock cycles to be retrieved from the secondary memory. You can understand that a CPU can never wait for the 7 lakhs clock cycles. So, no matter what, wherever the information is available, eventually the CPU has to access any information only through the main memory. For that, we need to transfer the desired block, the desired page from the secondary memory into the main memory. So, my main memory, which is of 8 blocks, can accommodate any of the 8 pages from the available 16 pages. I do have a total of 16 pages, 8 blocks, but CPU will have to use only the main memory. So, what CPU does? CPU will have to ask anything only to the main memory. Main memory should be able to provide anything which is asked by the CPU. For that, we should be able to make a transfer from secondary memory to the main memory. My main memory is capable of accommodating only 8 blocks from the available 16 pages. Will be capable of accommodating any of the 8 pages from the available 16 pages. In this instance, understand, the 000 block, that is the first block of main memory, contains 1000, that is the 8th block of 8th page of the secondary memory. Similarly, when it comes to the second block, it holds 000 page of the secondary memory. 010 block of the main memory contains 0111 page of secondary memory. 011 block of the main memory contains 0001 block of the secondary memory. So whenever CPU refers to an address, that address in the virtual memory systems is called a virtual address. So every time when an address is being located within the main memory, CPU needs to understand which page of the main memory is available in which block. Then the main memory will get accessed. So how it is going to happen, let us understand. This is the virtual memory example. In this example, my secondary memory is of 16 blocks and the main memory is of 8 blocks. So the block in the secondary memory is called as a page and a block in the main memory is called as a frame or a block. So now understand. This is the page table. Every time when the CPU is coming to the main memory, it needs to find out which block is available, rather which page is available in which block. For an instance, CPU wants to search for 0011 page. That is, it is the third page. Actually, it is the third page of the secondary memory. But CPU cannot access the secondary memory directly. It needs to access this page only from the main memory. If it is already available in the main memory, it is going to access it from the main memory. So in order to find out if the desired page is available within the main memory or not, CPU will need to use a page table. So understand how the page table is designed and constructed. Now, in order to design a page table, we need to go to the main memory and we need to ask some provision, some accommodation in order to accommodate this page table. So immediately main memory is going to ask you one question. Okay, fine, you want to design a page table. I will give you some space. But how much space you require? Immediately, we need to say that the total size of the main memory I require at this point of period equal to the number of pages. That means that the size of the page table will have as many entries as equal to the number of pages. What is the number of pages? The total number of pages are equal to 16. So, in a page table, I will have total 16 entries. So this is the page table. You can look at what you're witnessing on the screen is a single level page table. You can see understanding the single level page table is the simplest thing. Here on your screen, there's the first entry which is called a page number, which is going to index each and every page of the secondary memory. At that every index, we do have a field in which there is a frame number. That means that here when you have a look at the page or table, if you want to understand, have a look at this. 0000, which is going to index the page number. This page is available in this block. This page is available in this block. Now for this instance, 0010 of the page of the secondary memory is not available in any block of the main memory. So there won't be no entry here. And 0011 page is available in 100, and the other pages that are available in the main memory are 0111, 1000, 1001, 1010, and 1100. These are stored in the main memory in these blocks. Okay, so whenever there is a page is transferred to the main memory, immediately within the page table, there will be an entry made which holds the block number. For instance, 0101 has been transferred to the main memory into the first block. So 0101 against 0101, there will be a frame number in which this page is available. So at this instance, at this snapshot of the system, this is the actual status of the system. These are the pages that are available in these blocks of the main memory. Since main memory will only be able to accommodate 8 pages, any of the 8 pages, since the total number of blocks within the main memory is equal to 8. Now fine. So what is the problem? Let me tell you. Straight away you can see the problem. What we have just done, we designed a page table asking some space from the main memory. Main memory, whenever it is giving some space to you, it has a constraint. It will tell you, okay, fine, I'll give you the space, but use it potentially. If you don't use it potentially, my memory space will get wasted because I'm simple guy. My total size is pretty much limited, and that too you are rendering some space from myself. So whenever you use some space, please make it potential, make it use completely potential. But here you can see half of the page table is half of the chunks what you have obtained from the main memory, procured from the main memory, has already been wasted. Right? Now I'll tell you one more thing. Here we are discussing about a simple example. Consider an example like there are a total of 1024 pages and only 32 blocks. Page table entries will be equal to 1024 and the actual entries that will only be made is 32. Page table needs to have 1024 words and only 32 words will be filled up. Since main memory capacity is just 32 blocks, that means that the main memory can accommodate any of the 32 pages from the available 1024 pages. At that time, page table will be refined. The size of the page table will be equal to the number of the pages. The length of the page table will be equal to the number of pages within the secondary memory. A total of 1024 indexes, but only 32 indexes will have an entry. So the wastage is the biggest problem here. But we are rendering the place. We are procuring the place from the main memory. What is the size of the main memory? Main memory is a simple guy. No matter whether you talk about 2 GB, 4 GB or 16 GB, that should be utilized potentially, right? So there is a waste. This is the first problem that we are going to face. What is the second problem? Second problem is, as the page table size is getting increased, main memory finds it very difficult to provide you the contiguous locations, right? Main memory, when it comes to the data memory is non-contiguous. I'm not going to talk about non-contiguity right now, but understand one problem here. Finding out the contiguous free locations in the main memory will be very difficult as the size of the page is getting increased, size of the table is getting increased. It will be very impossible. It will be highly difficult to memory management system to provide those many contiguous chunks. Understand about an array. What is the problem with the array? Array size is 100, it can provide you. Array size is 1000, it can provide you. Array size is 10,000, it will hands up. No, I can't provide you. Of course, there are free 1,000 or 10,000 locations, but those are not contiguous. Same problem also comes with the table. Of course, table is simply, you can imagine as an array, right? So these are the two problems that we will face using a one-level page table. So what can we do? Here, problem is twofold. First one is, we need to avoid the contiguity. Second one is, we should be able to save the memory space. So here the virtual address, understand, in a virtual address in a virtual memory system, a virtual address will be sent by the CPU, referred by the CPU. A virtual address will have a page number. The first part of the virtual address will refer to a page number. Second part of the virtual address is the address within the page. Of course, every page is of several words, right? This is nothing but a page offset is nothing but a word address within the page. So here, in a single level page table, would you have only one table? Okay. This is the virtual address. Design implications are contiguous memory allocation. It will be practically impossible for the memory management system. Rather, there is an added burden. The time consumption will also be more here. Wastage. How much memory is being wasted? In this example, a total of half of the chunks are being wasted. In the other example of 1024 and 32, only 32 will be used out of 1024. So a total of, I guess, 992 locations are actually being wasted. So we can't afford this. So we will go to two-level page table. How the two-level page table will be constructed and designed? Let us understand. Now understand how a two-level page table is going to be designed, by which how we are going to save the memory space and also avoid the contiguity allocation. Now have a look at this. In the two-level page table, we will have an outermost table, rather outer page table, and an inner page table. Now, how many digits we do have in a page number? In a page number, we do have 4 digits. That is, let us say, for an instance, 0000. Now this page number, this page index will get divided into 2 fields. This field refers to the outermost page table. This field will refer to innermost page table. So every combination of the outermost value will have 4 combinations in the inner page table. So that is 00, 01, 10, 11. All these values will have corresponding 4 values within the innermost page table. So understand, in the outermost page table, we do have 4 entries. Each of the entries will have a pointer to an inner page table which has 4 entries. And of course, 00 has a pointer to first inner page table, 01 has a pointer to second inner page table, 10 has a pointer to third inner page table, 11 has a pointer to fourth inner page table. Now, what exactly we want? For an instance, CPU wants to find out where this 1001 page is available. For that, immediately, this by taking the first 2 digits, the computer system will locate this value in the outermost page table. In the outermost page table, this value has been located. Immediately, 10 taking at this, as we do have a pointer, immediately the control will go to the corresponding page table. 10, this all refer to the 10 page table, right? So immediately the control will take us to the inner page table of the outer page value, that is 10, in which in the inner page table, which value we require? 01 value we require. So 01 will get located. So the total, the outer value plus inner value is going to give you the location in which you may Find out a frame number. In this, if you do have a frame number, let us say it is available in 101 block. That means that this total 1001 is available in the 101 block. This is how the contiguity can be avoided. Here you can understand there is an outermost page table and there is an outermost page table and there are 4 inner page tables. You can understand these are not contiguous. For each inner page table, I do require 4 entries. That means that I don't require 16 contiguous entries within a page table. I just require 4 entries. Finding out of 4 entries will be fairly simple, right? So here I avoided contiguity. But where is the saving? I also promised you that we are going to save a lot of space, right? What is the saving? Here you can understand earlier page table size was just equal to 16 entries. But here one more page table has been added, which is the outer page table. It makes total 16 plus 4, 20. Now page table size is getting increased, right? How? Memory will get saved. Memory will be utilized more here. No. You need to think sensibly in order to understand this. For an instance, let us see. In the outermost page table, there is a value 10. This 10 will correspond to 0001, 1011. If you add all together, you will get these page numbers 1001, 1001, 1000, bigger pardon, 1001, 1010, and 1011. Let us see, none of these pages are available in main memory. If none of these pages are available in main memory, you don't find any entry here. If there is no entry here, this inner page table can completely be eliminated from the main memory. We don't require that inner page table within the main memory. This can completely be eliminated. So at any instance, if you think sensibly, many of the inner page tables will get completely be eliminated. Only those inner page tables which has a corresponding entry, which states the availability of the main memory, can only be present within the main memory. All the other inner page tables which doesn't have any entry at all can completely be eliminated. So this is how we will be able to save a lot of space within the main memory. For instance, let us say these two, and that is 01 and 11 outer page table has no corresponding entries in the inner page tables. These two are completely eliminated. So here, a lot of memory space has been saved, in addition to which we also address the contiguity problem. I hope you got it. That's it from the session. Anil Prasad Surampudi signing off. Thank you so much.